Good morning, fellow mathematicians, welcome back to another video. I could bet with you that my autofocus just jumped in. So if you would like to get rid of this autofocus, support me on Patreon. I'm trying to get a new camera. Link will be in the description. I can't turn this autofocus off. I tried everything. And I'm terribly sorry for this little spot of light. I hope it doesn't bother you too much. I'm trying to get the lighting as good as possible. That's the best I can do, I guess. Okay, let's get started with the video. Today we are going to tackle this bad boy here, this improper integral from minus infinity to infinity of sine of e to the x in terms of x. And we are going to use complex analysis on this one. So that's something new. I've never done it before on the channel, so that's great. So that's my first, as you might notice, and that means I'm trying my best to do this as good as possible. So let's go ahead and get started. At first we are going to start off with a simple u substitution. So let u equal to e to the x. So when we differentiate that, that would mean that du is equal to e to the x dx. Okay, but we know what e to the x is. It's just u, so that's great. So that's just u times dx. We can divide both sides by u, and then we know that dx is just u, 1 over u du. So that means that dx is just du over u. And we can plug all of this information in, so that's great. So we now have to find out our upper and lower boundaries. So if we plug minus infinity into this x right here, that would mean that u is equal to e to the minus infinity, so that's 1 over infinity, and that goes to 0, so that's great. And if we plug infinity into here, then that means that u just goes to infinity, because e to the infinity is just infinity. So that's great, we found that out. Now we can plug all of this information in. What we end up with is sine of u over u du. And this right here, my boys, is a well-known one in analysis and calculus. It's called the Dirichlet integral, and we are going to find it out today. This has been evaluated so many times already, but we are going to do it with complex analysis today, so that's going to be at least a little bit exciting. So how are we going to do this? When doing complex analysis, you want to find a contour, something like a closed area, and we are going to define it as follows at first. So we are going to take a look at a contour integral, so that's just an integral with a little circle in it, and we are going to call this contour C. Okay, so that's great. Of e to the I z over z dz, where z is a complex variable. Okay, so what can we do with this information? Let's define this contour somehow. So we are going to take a look at the upper half of the complex plane, right over the real axis. Okay, so we are going to define a semicircle that goes from some radius minus r to some radius r. And we are going to call this line on the outside, this arc, let's see, gamma, for example. Okay, so that's gamma. And this contour right here is C right now. But there's one little problem. We want to integrate over a singularity. What does that mean? If we would plug 0 into this u right here, that would mean it goes to infinity, it would diverge, so we don't want it. So in order to get rid of the singularity, that's called a removable singularity, we are going to take a little detour in our contour right here. We are going to look for the principal value of this integral. Okay, so our little detour is right here. I'm going to make it a little bit larger. It's really, really tiny, with a little radius of epsilon. Okay, so the radius of this semicircle that goes around the singularity in the origin is epsilon. Okay, so this really does help. So we can avoid integrating over the singularity right here with this little trick. And now we can define our way around this closed semicircle contour. So let's define it. So this right here consists of 4 parts. So we've got our gamma at first, and remember, we are going to go in this direction right here. So always counterclockwise. Okay, so that's great. So our gamma right here is just e to the I z over z dz, because we are moving along the complex axis somehow. Okay, and now our next part is plus Okay, so we are here now. That goes from minus r to 0 minus epsilon. So minus r to minus epsilon. And we are walking on the real axis right now. So those aren't complex, those values. We can just write them as x instead of z. Okay, so that's e to the ix over x dx. And our next path goes around this little semicircle at the origin. So it goes from minus epsilon to 0 plus epsilon, so that's just epsilon. Okay, so our integral from minus epsilon to epsilon, and this is complex again, because we are going upwards in the complex direction, you could say. So that's e to the iz over z dz, and plus another integral. And this integral now is just from positive epsilon to r. So we can plug this in. So this goes from epsilon to r, e to the ix over x dx, because we are walking along the real axis again. And here's an important lemma, and I'm just going to take it for granted. It's not a lemma, it's a theorem. Because we are avoiding the singularity at the origin, we can we could transform this right here, this integrand, into a power series, a Laurent or Taylor series. And also it's differentiable at every point because we are going around the zero. That means it's analytical. And when a function is analytical on a closed contour, this closed contour right here is just zero. So this is Cauchy's integral formula. So that's a great one. You should remember it. So this is analytical, this contour. So this whole bunch right here is just zero. That's great. And now we can bring some stuff to the other side and then we can move on. We already came pretty far. So what could we do now? Maybe we could bring some stuff to the other side. For example, we can exclude it from one side. So we can subtract this integral and this integral on both sides and see what we get. So that would mean that this is equivalent to the integral from minus r to minus epsilon e to the ix over x dx plus from epsilon to r the integral of e to the ix over x dx is now equal to, and I'm going to shorten this expression right now, this integral of gamma minus this integral of from minus epsilon to epsilon. Not minus epsilon to minus epsilon, that would be stupid. Okay, so we are just writing it in a little bit different way. We are now going to introduce a little substitution once again. And just for a little clarification so that no one gets confused, we are going to call this integral at the front, this left integral, I now. Okay, so we are going to play around with I. So I is equal to this integral. And now we are going to introduce a u substitution. So, no, not u, we are going to call it v. So let v equal to x, but with a negative sign. So we want minus v equal to x. You will see in a second why I'm doing this. So let's see what we get now. That would mean that minus dv is equal to dx. Okay, so let's plug everything in. So right now, this is, okay, so what's our upper and lower bound now? So if we plug minus r into here, that would mean that v is just r. And if we plug in minus epsilon into here, that would mean that v is just epsilon. Okay, and that's e to d minus iv now over minus v. And then minus dv times minus dv. So we can now cancel out those minus right here. So they would cancel out, this would become a positive sign. And what we end up with is just the integral from r to epsilon of e to the minus iv over v dv. And now we can factor out a minus 1 so that we can switch around those upper and lower bounds right here. So let's factor out a minus 1. So it goes from epsilon to r. And I want you guys to remember that this integral right here is still our I. So we are dealing with a dummy variable right now. So that's an important concept when you're dealing with integrals. And it doesn't matter if there's a v here or an x or a tree or whatever you might wish. Okay, so we could safely say that this v is equal to our original x once again. So we can do this. And when we plug this in, we will get the following. Okay, so like I said before, we can just plug this integral once again in. So that's an equivalent approach. So now our integral. And we are going to say that v is x again. So this is now minus the integral from epsilon to r of e to the minus ix over x dx. So many people struggle with this concept of dummy variables. I don't know why they do, but many people struggle with it. So that's something that holds. And now the upper and lower bounds are equal. So we can bring those together, and also our denominators are equal. So we can just add those integrals together. So they are now just the integral from epsilon to r of e to the ix minus e to the minus ix over x dx. And this right here is pretty awesome, because I want you guys to remember how we can express the sign of something in terms of the complex exponential function. So the sign of x is nothing else than e to the ix minus e to the minus ix over 2i. And if we multiply everything by 2i on both sides, that would mean that this numerator right here is just sine of x times 2i. So we can rewrite this. So that's just the integral from epsilon to r of 2i times the sine of x over x dx. And this right here is nearly our integral right here. So that's pretty great. Okay. You could also say that this is u instead of x. Don't get confused by this. Those are just variables. So what can we do now? So our integral would be equal to this one right here if we would divide everything by 2i, and also we would take the limit as epsilon approaches 0 and the limit as r approaches infinity. So let's just write this out. So that means if we take the limit as r goes to infinity and epsilon goes to 0 of this integral. So that's 2i. The integral is linear, so we can do this from epsilon to r of sine of x over x dx. Okay, and this would then be equal, if we apply the limit on this side, to the integral from 0 to infinity, 2 times I, the integral, of sine of x over x dx. Okay, but if we apply the limit on one side, we have to also apply it on the other side. So let's now take the limit as r goes to infinity of minus the integral of gamma, because gamma isn't dependent on epsilon. Gamma goes from r to minus r. So we can safely assume that we can leave out the limit as epsilon approaches 0 on this one. And also minus the limit as epsilon approaches 0 of this other integral from minus epsilon to epsilon. And here's one important lemma you should know for this. We can apply Jordan's lemma to this function right here, because Jordan's lemma states on a semicircle, if the outer arc goes from r to minus r and those r's become arbitrarily large, then this just vanishes. This goes to 0. So we get rid of this. And what we end up with right now is just 2 times I times the integral from 0 to infinity of sine of x over x dx is just minus the limit as epsilon goes to 0 of this integral right here. And now we are going to finish this one off. To finish this one off, we need a new substitution. So that one's kind of counterintuitive. You have to play around with substitutions. But most of the time you want to introduce some exponential function to make it work a little bit better. So we are now going to let z equal to epsilon times e to the I phi. Okay, so when we differentiate that, that would mean that dz is just. And now we are differentiating in terms of phi at this point. So that's I times epsilon times e to the I phi, d phi, d phi. Okay, what could we do now? At first we could rewrite this integral right here. So this is just now minus the limit as epsilon goes to 0 of. And now we have to find out our upper and lower bound. So if we plug minus epsilon into here, that would mean for minus epsilon, that minus epsilon is equal to epsilon e to the I phi. The thing is, we are going to say that epsilon is greater than 0, so we can safely rewrite this as minus 1 equals to e to the I phi. And I want you guys to remember what e to the I phi is also. So e to the I phi is just the cosine of phi plus I times the sine of phi. And now we somehow need to get minus 1 on this side. So how do we get minus 1? Well, what is a minus 1? So, for example, if the... I want you guys to notice that this is just a real function on this side. So we want this to become real, at least. So we need to get rid of this part right here. So for example, if we plug in 0 into here, that would mean that this sine would become 0, but the cosine would become positive 1. So that doesn't work. So our next approach would be pi over 2, doesn't work. And then it would go to minus pi. To pi, I'm sorry. If we plug in pi into here, that would mean that the sine would go to 0, so that would be great. And also our cosine of pi is minus 1. So our lower bound is pi. So that's great. And for our upper bound, we can plug in epsilon into here. So that's the same reasoning. So we want to get 1 on this side. Right now. That's what I said before. If we plug in 0 into here, that would work for our cosine. So our upper bound is 0. And we are going to take the principal branch of this complex number here. Okay, so this is our new integral. And now we are going to plug all this new information in. So right now, our numerator is e to the I times epsilon to the e to the I phi over epsilon e to the I phi. Okay. And the next thing, we know what our dz is. dz is just this function right here. I times epsilon times e to the I phi d phi. And the great thing is, this cancels out. So right now we end up with minus the limit as epsilon goes to 0 of the integral. And we can distribute this minus into this integral right here if you like. So we are just changing the upper and lower bound. So it goes from 0 to pi. And now it's e to the I epsilon e to the I phi times I times d phi. And the upper and lower bound aren't dependent of epsilon anymore. So we can safely bring this limit into the integral. And if we let epsilon approach 0 right here, that's just 1. So our integral is just the integral from 0 to pi of I d phi. I d phi. That sounds great. And we can integrate this, so that's pretty simple. So this is just our phone started off. So this right here is just I times phi from 0 to pi. What a great rhyme. Okay, if we plug this in, the lower bounded would just go to 0, so this is just I times pi. And this is great. This is really great. So our final solution is now. So this is our integral right now. And the good thing is, this one right here will be strictly real, not complex anymore. So that's what was to be expected. So we can cancel this I out on both sides, divide I on both sides, and also we can divide by 2 on both sides. So what we end up with is just that our integral up here, the integral from 0 to infinity of sine of x over x dx is just pi over 2. And this is indeed the value for this integral. So that's great. We found this out. Whew, that was quite some work. And well, if you guys like this video, please like and subscribe. I hope I did this kind of well. It was my first attempt on complex analysis. But if you like this video, please like and subscribe and recommend me if you like. And up until the next video, Have a flammable day. See ya.